All right. And of course, if you have a question, don't hesitate to type it in the chat or unmute your mic, and I'd be happy to answer it. So this chapter deals with alkanes and cycloalkanes. So one thing I want you to remember is that I know we went over the functional groups in chapter 2, but alkanes and cycloalkanes are not a functional group. Those are not functional groups. Not a functional group. Either of them. Okay, alkenes and alkynes, those are functional groups. Aromatics, those are functional groups, but alkanes and cycloalkanes are not functional groups, but they are going to be the focus of this chapter. However, alkanes and cycloalkanes come from a broader class of compounds called hydrocarbons, and those are compounds that are comprised of hydrogen and carbon only. So they have some kind of formula CXHY. If you look at an alkane like ethane, you can see that the formula follows CnH2n plus 2. So N is 2, 2 times 2 is 4, plus 2 is 6, so C2H6, okay? If you have an alkene, you can see that it follows the formula CnH2n. There's 2 carbons, so 2 times 2 is 4, so C2H4. If you have an alkyne, like acetylene, it follows the formula CnH2n minus 2. So if you take 2 times 2, which is 4 minus 2, gives you 2, so C2H2. And then benzene has a formula of C6H6, okay? Anyhow, so again, ethylene is an alkene. Acetylene is an alkyne. Benzene is an aromatic. Ethane is an alkane. They are all hydrocarbons. However, the alkene, alkyne, and aromatic, those are functional groups. And the alkane, which is going to be a lot of the focus of this chapter, an alkane is not a functional group, but it's a special class of hydrocarbon that we call saturated. It has the maximum number of hydrogens possible or the number of carbons we have. So if you look at the formula, CnH2n plus 2, you cannot put more than 6 hydrogens with 2 carbons. So if somebody said, could there be something like C2H9, it's impossible. You could not have more than 6 hydrogens when you have 2 carbons based off of this formula. So when it comes to naming alkanes, okay, you would have talked a lot about naming in general chemistry when you learned how to name things like, phosphorus trichloride, okay, or ammonium carbonate, stuff like that. Well, organic compounds, a lot of them have common names, all right? If you think about medicines, a lot of them have trade names, marketed names, but many organic compounds have common names, so many that it can be difficult for students to memorize them all. But there's only a few that you need to know in this class. But let me just show you a little background. It says, in 1892, as the number of known molecules grew, chemists all over this entire planet that we call Earth decided there has to be a systematic way to name these molecules. Now, common names. Historically, common names were used. If you look at this first compound here on the left, this is called formic acid. It's isolated from ants, and the Latin word for ant is formica or formica. I'm not sure how that's pronounced. But again, that's a common name, formic acid. It also has a systematic name, which is methanoic acid, but formic acid is still used. The next one is urea. You can probably guess where that comes from. It comes from urine, so urine, urea. The next one is morphine. If you've ever wondered where the name morphine comes from, it's named after Morpheus, who was the god of dreams. And then it says here that barbituric acid is named by Adolf von Baer, and he named it, it says here, named it in honor of a woman named Barbara. I always read that he was infatuated with this woman and just named the compound after her, barbituric acid. So again, once organic chemists found, so many, molecules, once we get into the thousands of molecules, they said, well, we need a systematic way of naming these. And so what they came up with was the IUPAC nomenclature system. So IUPAC, if you don't remember, this stands for the International Union of Pure and Applied Chemistry, okay? It is it's used all over the entire Earth to name compounds. So the way that we name compounds using IUPAC nomenclature is the first thing is we find the longest carbon chain, then we name substituents, and then we provide a location for those substituents And for the location, we use what we call locants, which are essentially just numbers. Okay, and I'll show you how to put all these three together. But first of all, when we're finding the longest carbon chain, okay, you've got to remember that it's not always linear. Okay, it's not going to be spelled out for you every time. Sometimes you have to find it by trial and error. Let me show you what I mean. So let's say you have this compound here. It says find the longest carbon chain. If I asked you to name this compound in the red circle, you would try to find the longest consecutive chain of carbon. So let's say you grabbed your pencil. Let's say Isaac's doing this. He says 1, 2, 3, 4, 5, 6. There's the longest chain. Good. And then somebody else comes along and says, no, hold on. 1, 2, 3, 4, 5, 6, 7, 8. There we go. There you go. 8 carbons in a row. And then somebody else says, no, you're both wrong. Okay. It's actually got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So the way you're going to find this, okay, find by trial and error. Okay. You keep looking until you find the longest carbon chain. Again, it's not always going to be in a straight line like this. You have to keep looking. You're like, really have to keep looking and looking until I find it? Yep. Okay. Everybody does. It's part of being an organic chemist, is looking over and over and over. You might have even found something like this, 1, 2, 3, 4, 5, 6, 7, 8. I think that's the one I highlighted before. Anyhow, but again, the longest chain has 9 carbons. So this is what we call the parent, or sometimes they call it the principal chain. Principal, parent, or principal. Our textbook uses parent, so the parent chain. And then everything that comes off of the parent chain, okay, we call these branches coming off of the chain. So these are branches. Everything I have circled, those would be branches, okay? So after you have to identify the parent chain. So again, longest consecutive chain of carbons. Here's a rule that I forgot to go over. If there's 2 chains that are of equal length and they're the longest ones, the one that is going to be your parent is the one that's got the most substituents, okay? So take a look at both of these let's number them. They have 1, 2, 3, 4, 5, 6, 7. Here we have 1, 2, 3, 4, 5, 6, 7. Okay, so we found 2 different chains. They have 7 carbons. They're the longest possible chains. However, if you look at the one on the left, you see it's got 3 branches or substituents coming off of it, whereas the one on the right only has 2. So we picked the one that has the most substituents attached, okay? So let's highlight it here. We'll put longest chain, okay, with the most substituents attached. All right, so now that we've got that, we have to come up with parent names. Okay, so if we have only 1 carbon, that's going to be so we would say methane for 1 carbon. So we would just write that as CH4. That's the simplest possible organic molecule on the planet Earth. There's no bond line structure that you can draw for it. You can't just put a dot and say, there you go, CH4. It doesn't exist. If you have ethane, right, that's going to have 2 carbons, so CH3, CH3. If you have propane, it's going to go CH3, CH2, CH3. Then to butane, 1, 2, 3, 4 carbons. Pentane, 1, 2, 3, 4, 5. Hexane, 1, 2, 3, 4, 5, 6. Heptane, 1, 2, 3, 4, 5, 6, 7. Octane, 3, 4, 5, 6, 7, 8. Nonane, 1, 2, 3, 4, 5, 6, 7, 8, 9. And decane, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There you go. So those are your first 10 parent chains. Methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. You must memorize these. You must know all of these. Okay, there can't be any question in your mind about, if I have 3 carbons, is that a butane? Or no, you have to know that's a propane. All right. Now, I think the first 4 are the hardest ones to memorize, because once you get to pent, you can think of a pentagon, which has 5 sides, hexagon, hept. That one's kind of tougher, I guess. But in French, the word for 7 is sept, which is S-E-P-T. So I kind of draw the connection between E-P-T. Octane, right? Octagon. nonane kind of sounds like nine, and then decane, well, you know what a decade is. So there you go. If you're wondering about chains that are longer than 10 carbons, yes. If you have 11, it's undecane, 12 is dodecane, 13 is tridecane, tetradecane, pentadecane. Then you go to icosane. If some of you have studied biology or advanced biology, you might have heard of the icosanoids. So icosanoids, okay? I'm not going to get into the icosanoids like thromboxanes and leukotrienes, but those are important in biochemistry. Then you get the tricontane, tetracontane, pentacontane, and then hectane. You don't have to memorize the ones on this slide. I don't think you do. You have to memorize the ones on this slide, okay? I think that knowing undecane and dodecane are kind of handy because sometimes you find compounds that have 11 or 12 carbons. And again, icosane, right, has 20 carbons. Well, there's icosanoids, which are interesting in biochemistry. But anyhow, it says here, what if you have cyclic compounds? So if you have a cyclic compound, you count the number of carbons in the parent and you put cyclo in front of it. So here we have a total of 1, 2, 3 carbons. So it's not propane, but cyclopropane. The next one we have 1, 2, 3, 4. So it's going to be cyclobutane. 1, 2, 3, 4, 5. So cyclopentane. And then if you had 6, what do you think you'd call it? Can anybody guess what this compound would be? Could anybody guess the name of that compound? Go from cyclopentane to cyclohexane. Yeah, absolutely. Perfect. Cyclohexane. Awesome. Yeah. And then you have cycloheptane, cyclooctane, so on and so forth. Just keeps going. So let's get some practice here and see if we can identify the parent or the longest chain in each one of these compounds. So if we take a look at the first one, how many carbons are there in the longest chain in here? Did anybody identify the number of carbons in the longest chain? It's not 5 in this one. There's a chain that's longer than that. 6, isn't it? Yeah. So if you were to number like this, 1, 2, 3, 4, 5, that's not the longest chain, is it? Right? The longest chain goes like this. 1, 2, 3, 4, 5, 6. So there's 6 carbons in the longest chain. And then you have one branch or substituent right here. All right. A rule that we're going to look at in a few minutes is, do you start numbering with 1 here or do you start numbering with 1 here? Well, the answer is, would you start numbering at the end where the first substituent gets the lowest number. So where if I start numbering in yellow, you can see that that group in blue is on carbon 3. If I had done it starting here, I'd have 1, 2, 3, 4. So then the first group, the only group, would be on carbon 4. Well, 3 is a lower number than 4. So that's why you'd start numbering where the yellow highlighter is. All right. Did anybody find the longest chain in the next one? Anybody? There's 7, isn't there? How many? Hey, no, you don't go from the top to the bottom. You go from the longest chain, but you start on the end where the first substituent gets the lowest possible number. So I'll show you that on another slide. So for the next one, Brooklyn, you're right that there's 7 carbons, but you could do it like this. You could say 1, 2, 3, 4, 5, 6, 7. Or you could do it like this: 1, 2, 3, 4, 5, 6, 7. Does anybody know which one is correct? Is it the numbering in red or the numbering in blue? Because there can only be one correct answer here. It's the one in blue, isn't it? Yeah, because you have more substituents, right? The numbering in red only has 1, 2 substituents, but the numbering in blue has a total of 1, 2, 3 substituents, right? So the numbering in blue is correct. Great. Awesome. Oops. Didn't mean to do that. All right, so that's good. So we'll put here 7 carbons for this one. Anybody identify the longest chain, the parent in the last one? Not a trick question. Anybody get the next one? So we have to only go in a chain, right? So the next one has a total of 7, exactly. So we start here. Let's see, 1, 2, 3, 4, 5, 6, 7. Okay, so you can't go through a chain, right? So this is a chain, this cycle, right? We go 1, 2, 3, 4, 5, 6, 7, but you can't go backtrack over a carbon a second time and then say 8 or something like that. You can't do that, okay? So you can only go around a ring one time, all right? But remember, there wouldn't be 10 carbons in here. There would only be a total of 9 carbons in the entire thing, right? But these ones are sort of 8, 9, like that, okay? But that would be the longest chain, would be 7 carbons. All right, so how do you get good at this? What do you have to do? Practice it over and over and over. So with that in mind, we identify and name the substituents. And so if we have a CH3 group, okay, you probably recognized a few of those today. We call that a methyl group. If we have CH2, CH3, we call that an ethyl group. If we have CH2, CH2, CH3, we call that a propyl group. Now you could also draw the bond line structure, right? If you just have a line coming off, that would be a methyl. If you have CH2, CH3, that would be an ethyl. If you have 1, 2, 3, like this, that would be a propyl. If you're wondering what the squiggle is, the squiggle is just showing where I'm starting from, okay? If you have 4 carbons, so if you have 1, 2, 3, 4 in your chain, that would be a butyl. If it's got 1, 2, 3, 4, 5, that would be a pentyl. If you have 1, 2, 3, 4, 5, 6, that would be a hexyl, heptyl, and octyl. Okay, the ones that are going to come up the most are going to be methyl, ethyl, propyl, and butyl. Okay, those will come up by far the most. So somebody asked me, I think you're talking about this question right here. They said, why can't you start at the end one you put the number 8 on? Because you can't go through a ring, okay? You can't go from outside of a ring and then into a ring. If you have a ring, you can only stay in the ring. You can't go outside of the ring. So the ones that are going to come up the most will be methyl, ethyl, propyl, and butyl, but you do have to know the other ones as well. Now, if we take a look at this compound here, we see our longest carbon chain has a total of, let's just number it. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is some kind of decane, okay? The reason I started numbering on the left-hand side is because we have 1, 2, 3, 4. We have a substituent at carbon number 4. It's an ethyl group, right? Because it's CH2, CH3. At carbon 5, we have a propyl because it's CH2, CH2, CH3. And then at carbon 7, we have a methyl because it's CH3. Now, if you're wondering why couldn't I start numbering from the right-hand side here, it's because if you did, you'd have 1, 2, 3, 4. You'd have your first substituent at 4, but then you keep going. And if you went to carbon 5, there's nothing on it. But if you look at the numbering in red, at carbon 5, there's something on it. So you go for the tiebreaker, okay? Whichever one breaks the tie. So there you go. Our longest chain is a decane. It has 10 carbons. We've got an ethyl group at carbon 4. We've got a propyl group at carbon 5, and we've got a methyl group at carbon 7. So again, the groups that are going to come up the most are going to be methyl, ethyl, propyl, and butyl. Now, it says a ring can be either a parent or a substituent depending on how many carbons are in it. If the ring has more carbons than the substituent, then it is the parent. And if the ring has less carbons than the parent, then it is a substituent. So remember, you can't number a ring and then go outside of the ring, and you can't go outside of a ring and then into a ring. So if we look at the parent here, you can see it's got a total of 1, 2, 3, 4, 5, 6 carbons in it. So it's some kind of cyclohexane, but then we've got a propyl group here, right? CH2, CH2, CH3. So this is propyl cyclohexane. Whereas here, our longest chain has 1, 2, 3, 4 carbons. There's only 3 carbons in this ring. So this is some kind of butane. And instead of calling this cyclopropane, we call it cyclopropyl. Okay, so we just name it as a substituent. So 1 cyclopropyl butane. The one refers to the fact that it's at carbon number 1. All right, if it was at carbon number 2, it would look like this. Okay, this you would call this, so it's not a good cycle of propane, is it? Fix that. Come on. You would call this 2 cyclopropyl, cyclopropyl butane. Okay, 2 cyclopropyl butane, like that. All right. Now, if you have a complex substituent, I'm going to skip this for now and come back to it later. Okay, we're going to stick with the common substituents for now. Okay, so there are a total of about 8 alkyl groups that come up a lot in this class. I'll write them down here just so you have a laundry list somewhere. You have to know methyl. I'll just write down the names. You have to know methyl, ethyl, propyl, isopropyl. You have to know butyl, isobutyl, tert butyl, and sec-butyl. Sec-butyl. Those are the alkyl groups that are going to come up the most in this class. A methyl group only has 1 carbon in it. An ethyl group has 2 carbons in it. Propyl and isopropyl both have 3 carbons. And then butyl, isobutyl, tert-butyl, and sec-butyl, they all have 4 carbons in those groups. So if we take a look at propyl, right, it's got CH2, CH2, CH3. So what's the formula of this part? It's C3H1, 2, 3, 4, 5, 6, 7. So besides arranging it that way, you could also arrange it like this so that you have a CH here, a CH3 here, and a CH3 here, and we call that an isopropyl group. So now we have methyl, which was CH3. We have ethyl, which is CH2, CH3. We have propyl and isopropyl. So there's half of them done. Now when you get into the butyls, okay, if you look at butyl, which is on the far left here, it's comprised of CH2, 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 CH3. And so what's the formula for all this? It's C4, 1, 2, 3, 4, 5, 6, 7, 8, 9. C4H9. And so we can arrange that a total of 4 different ways. We can have a butyl, a sec-butyl, an isobutyl, and a tert-butyl. I think there's no easy way to remember these, but if you remember the isopropyl, if we go back here, the isopropyl ends with two methyl groups coming off at the end, like this. Okay, and if you look at the isobutyl, it's got 2 methyl groups coming off at the end. If you think of sec-butyl, you think of secondary or 2, the carbon, the first carbon, is attached to 2 carbons, so 2 for secondary. And then tert sounds like tertiary, right? And the carbon coming off of the chain is attached to 1, 2, 3 carbons. So those are some ways you can memorize tert-butyl, sec-butyl, isobutyl, and butyl. Also, you probably noticed that tert-butyl and sec-butyl have a hyphen in them, whereas isobutyl does not. And that is actually going to be very pertinent in a few seconds when we start putting things in alphabetical order. So to rehash, what are the 4 groups that you're going to see the most? Methyl, ethyl, propyl, and isopropyl, butyl, isobutyl, tert-butyl, and sec-butyl. Okay, so you have to know all of these substituents. And so now let's go through some more rules. Again, we number the carbons in the parent chain, and we number it in such a way that we give the first substituent the lowest possible number. Okay, the first substituent. We don't start adding numbers together and trying to do complex mathematics to think about, okay, which one gets the lowest number or something like that. You just go for the first substituent and give it the lowest possible number. So if we have 1, 2, 3, 4, 5, like this, if I was to number starting over on the right-hand side, 1, 2, 3, 4, then it would be 4 methyl pentane, and there's no such thing as 4 methyl pentane. It doesn't exist. The proper name is 2 methyl pentane because the numbering should be in such a way that you start in such a way that you give the first substituent, which is your methyl, the lowest possible number. Now in the next one, in this one here, 3-methylpentane, would it matter if we started numbering from the left or the right on the longest parent chain in this particular case? Would it even matter here? Could anybody answer that? Nope, exactly. You're right. It doesn't matter at all, does it? Now, if you're wondering why would that be, how did they know that? The reason why is if I started numbering here, 1, 2, 3, 4, 5, my methyl group is still going to be at carbon 3. So sometimes it doesn't matter if there's symmetry in the molecule, but it usually does. There we go. Now, again, you notice that the 2 represents carbon number 2. You notice that the 3 represents carbon number 3. You probably also notice that numbers and letters, so I'll put here numbers and letters are always separated by a hyphen, okay? Always separated by a hyphen, numbers and letters. If you have numbers and numbers, they're separated by a comma. So we could put that in here too. So we could say numbers and a number. I'll just put here number, singular, and a number. Those are always separated by commas. All right, there we go. So guidelines to follow. And I've gone over a couple of these already just to expose you to it. But the first one is you number the chain in such a way that you give the first substituent, okay? The first substituent gets the lowest possible number, whatever it is, okay? So you see the way on the left is correct because our first substituent is carbon number 2. The one on the right is incorrect because the first substituent is carbon number 6. Wrong. All right, so how would you name this compound? Well, the parent is 7 carbons, so it's some kind of heptane. And so could anybody help me out with the rest of it based off of what you've seen so far? How would you do the rest of this one? So it's some kind of 2-methylheptane, exactly. Because you have a methyl at carbon 2, so 2-methyl heptane. And letters, we don't separate by spaces or anything. It's just one word, 2-methylheptane, like that. There you go. So there you go. Thanks a lot, Aaron. We've started naming our first organic compounds. All right, feels good. All right, next one is when you have multiple substituents. Remember, no mathematics involved. You number it in such a way to give the first substituent the lowest number possible. Don't worry about everything else. You're like, oh no, well, these numbers add up and they're too high. We don't have to add numbers at all. You just give the first substituent the lowest possible number. You see on the left, the first substituent is that methyl group. Over on the right, the first substituent are these 2 methyl groups. Well, 2 is a lower number than 3. Got nothing to do with the number of the other groups. It's whichever one gives you the first substituent, the lowest possible number. So in the compound on the left, we have a methyl group at 2, 5, and 5. And so the way you would determine, or you would denote rather, that there are 3 methyls is you would use tri, the prefix tri. So you'd call this, I'll just use my black pen here. There we go. You'd call this compound 2, 5, 5 trimethyl heptane. Trimethyl heptane. Like that. 2,5,5 trimethyl heptane. All right. If there is a tie, so if you end up with a tie, like is shown here, you have 1, 2, and then here you have 1, 2, and you have a substituent on both of them. Then you keep going. So on the one on the left, you go 1, 2, 3. Okay, there's something on carbon 3. The next one, your next substituent doesn't come till carbon 5, so a 3 beats a 5, and there you go. So now we have methyl groups of carbons 2, 3, and 6 in this compound. So this would be 2, 3, 6 trimethyl heptane. 2, 3, 6 trimethyl heptane. What if you have halogens? Well, let me walk you through them. There's 4 halogens. There's fluorine. Its prefix is fluoro. There's chlorine. Its prefix is chloro. There's bromine. Its prefix is bromo. And there's iodine, which is iodo. All right. So we have those 4, fluoro, chloro, bromo, iodo, and we use alphabetical order. So in this case, we have substituents, it's carbons 1 and 5. Over on the right, we have substituents at carbon 1 and 5. Well, bromo is going to be chloro. It's not based off of, it's not based off of, what am I looking for? Atomic number. It's based off of alphabetical order. B comes before C in the alphabet, so we use alphabetical order. So we use A to Z, okay? So we call this 1-bromo, 6, no, sorry, 5-chloro, chloropentane is how you would name that compound. 1-bromo, 5-chloropentane. All right, let's see. What if we have a chain? Okay, let's say, or sorry, a cyclic compound, and that's our longest chain. In that case, we're going to follow the same rules. We want to give the substituents the lowest possible numbers. So if we look at the compound on the left, you've got 2 substituents here, whereas you've only got 1 substituent here. So 113 is going to be 133, right? We always go for the tiebreaker. So this compound on the left would be called 113 trimethyl cyclohexane. All right, give me a thumbs up if you're with me on that. Any questions about the rules we covered so far?
Yeah, just real quick, why would you not start underneath and do the chain of 5 underneath?
Chain of 5. You mean like this?
Yeah.
Because that's not a chain, okay? So we have to go through the whole thing that's attached together in a ring, which is a total of 6 carbons. Does that make sense? Those 6 carbons in that yellow highlighter are all attached to each other. So that would consist of a parent chain, right? All 6 are attached together. All right. If you had 5 carbons in a ring, it would look like this, right? But since we have 6 all attached together, we have to take the whole thing together. And then you can't go outside of a ring and you can't go into the ring. So you can't say 1, 2, 3, 4, 5, 6, 7, 8, or something like that. You can't do that. You can't go outside of the ring. Once you're in the ring, in it to win it. All right. Does that help? Okay. I hope so. All right. So now, what did we come up with here? We go from number 1 to number 5. Anyhow, so from number 1 to number 2, it says here, put a number and name of each substituent before the parent. Put them in alphabetical order. So going back to the alphabetical order, I'm going to cover something here. If you have isobutyl, so when you have the prefix iso, you alphabetize according to the letter I. But if you have tert hyphen butyl or sec hyphen butyl, you alphabetize those according to the letter B. So you ignore the prefix tert and you ignore the prefix cyclo. Sec and tert. Let's see here. Also, if you have the prefix cyclo, so let's say you had something like cyclobutyl, there's no prefix or there's no hyphen in there, and so you would alphabetize according to the letter C. So only when you have the hyphen, you ignore the prefix. You don't alphabetize using the prefix. Now, if you have more than 1, let's say you have 2, you would use di. If you have 3, you would use tri. If you have 4, you would have tetra, penta, and then hexa, hepta, etc., etc. All right, we also ignore the prefixes di and tri, tetra, penta. So let's say you had tetra, oh my god, tetramethyl. Okay, you would alphabetize according to the letter M. Right? Hopefully that makes some sense. All right, so with that in mind, you identify the parent chain. You identify and name the substituents, so methyl, ethyl, propyl, isopropyl, terbutyl, etc. You number the parent chain in such a way that the first substituent gets the lowest possible number. If there's a tiebreaker, you have to go for that. Assign a locant, which is nothing more than a number to each one. So is it a 2-methyl, a 3-methyl? So this is just a number. And then you list the numbered substituents in alphabetical order before the parent name, and you're done. So that's how we name a number, name and number a compound. So let me just show you one quick example here. So this compound, you might look at this and say, oh, wow, that's so difficult to name. Well, actually, it's not that bad if you break it down. You can see that I numbered the longest carbon chain here, which is the 6-membered ring. And then we have three types of substituents. We have a tert-butyl group here. We have an ethyl group, okay? And then we have 2 methyl groups here. So we have 2 methyl groups. So our parent is cyclohexane. The tert-butyl group is at carbon 1. Why did I start numbering up here? It's because if you start there, your numbers are 1, 2, 3, 4. Okay, if I started numbering here, 1, 2, 3, 4, 5. So then I'd have 1, 2, and 5. Well, 1, 2, and 4 beat 1, 2, and 5. So if I put it all together, I've got a 1 tert-butyl, a 2 ethyl, and a 4,4 dimethyl. So in alphabetical order, I'm going to alphabetize according to the letter B, the letter E, and the letter M. So when I put this all together, what do I get? I get, let me see, is there a mistake in this? There's a mistake in this, actually. Let me fix it. Let me show you what the mistake is. I'll show you quickly. So there's nothing wrong with that. It's the numbering. I just noticed there's a mistake in this, and this is from the publisher. So I'm going to block that out, block that out, block that out, block that out, block that out. Did anybody notice there's a better way to number this? I did. Okay, there's a better way, and that is actually to start down here. It would be 1, 2, 3, 4, like that, because 1, 1, 3, and 4 are going to beat 1, 2, and 4, and 4, right? The 1 beats this 2 in the second position. So this is actually the right way to do it. So this should be a 4 tert-butyl. This should be a 3 ethyl, and this should be a 1 and a 1 methyl. So this would be a 1, 1 dimethyl. So now, again, going back to alphabetical order, I've got B, E, and M. So it should be 4 tert-butyl, 3 ethyl, 1, 1 dimethyl cyclohexane. So I'm going to have to go back in the slides and fix this one. I just noticed that now. Anyhow, let's try one that doesn't have a mistake in it. We'll try this one here, okay? 4.8b, you have the solutions to this one too in the solutions manual. Could anybody tell me what's the longest carbon chain in 4.8b? And there's no trick questions or anything. Remember, a cycle counts as one chain. You can't go outside of it. Could anybody tell me how many carbons are in the longest chain? 6, exactly. Exactly, there's 6 carbons, right? Because I have 6 carbons in the ring, 1, 2, 3, 4, 5, 6, but I only have 4 carbons out here, 1, 2, 3, 4. So the longest chain has 6 carbons. Okay, I started numbering 1 at this position. Why? Because that's where the substituent is, and I want to give it the lowest possible number. Can anybody identify this substituent? It's C4H9. It's one of the substituents we saw. If you have to go back in your slides, take a look. It's in, yeah, thanks, Isaac. It's the sec-butyl, isn't it? Yep. So no locant required. This would just be sec-butyl, cyclohexane. Okay. You don't have to put a 1 before the sec-butyl because that's redundant. There's only one substituent. And so it's just sec-butyl cyclohexane. It's implied that the substituent is going to be at carbon number 1. All right, what about the next one? What about B? Could anybody tell me what the longest chain is in this one? What's the longest chain of carbons in this guy? Anybody find the longest carbon chain in this one? Thanks, Aaron. Yeah, it's 8, isn't it? Okay, so there's 8 carbons in the longest chain. If I highlight this carbon in red and this carbon in blue, should I start numbering where the carbon in red is or the carbon in blue? Exactly. where the red one is, right? Because then I give the first substituent the lowest possible number. If I went with blue, I'd have 1, 2, 3 is where I have my first substituent. But if I go with red, then I have 1, 2, 3, 4, 5, 6, 7, 8. So this is some kind of octane. So we can just write a list. The parent is octane. We have a 2-cyclohexyl. We have a 4-ethyl. And then we have a 5,6-dimethyl. 5,6-dimethyl. Like that. There we go. So now we're going to alphabetize our substituents. So we have C for cyclo, E for ethyl, and M for methyl. Remember, we ignore the di, tri, tetra, and all that stuff. So I have a 2-cyclohexyl, so I'll scribble it down here at the bottom. I've got a 2-cyclohexyl, 4-ethyl, 5,6-dimethyl octane. There you go. So 2-cyclohexyl, 4-ethyl, 5,6-dimethyl octane would be the name of that compound. So there you go. Now we've covered the rules on how to name organic compounds. So the next thing we're going to cover are bicyclic compounds. Okay, bicyclic compounds is